Hi and welcome to my Physics Online video lecture series. Today's video we're going to be talking a bit about projectile motion. So this is a continuation of my previous set of videos that discussed motion in 2 and 3D. This one being projectile motion, we are looking at a two-dimensional type of motion. You will recall that in the previous video I already discussed how to approach two-dimensional motion, and also that we've discussed previously how to add vectors in 2 dimensions using either Cartesian basis, polar basis, meaning algebraic or geometric method. Collectively, what this means is that you expect to either be doing tip-to-tail vector resolution, which is entirely possible to do, but I'm not going to for this video. Again, because of the fact that I'm using a little draw pad, not a screen to write on, and when I draw stuff on the draw pad it doesn't scale exactly to the screen, so it's rather difficult for me to do vector resolution using the geometric method. Therefore we're going to do the algebraic method. One consequence of using the algebraic method is that you get more equations. So ultimately, one set of equations for each coordinate. That is, you'll have one set of equations for the x's and one set for the y's. So we expect to have, on the one hand, something that says x is equal to 1/2 ax t squared plus v initial x t plus x initial, assuming of course a constant acceleration in the x direction. We also expect that the velocity along x will be the acceleration along x times time plus the initial velocity along x. And we also have the time-free version of this, 2 times the magnitude of x acceleration times the change in x should be vx final squared minus vx initial squared. And then we should expect a whole second set of equations. So this right here is one set of equations. This goes with the x's. We expect the whole second set of equations to go with the vertical part. Y equals ay t squared plus vy initial times time plus y initial. And then we similarly expect vy to be ay times time plus vy initial, and 2 ay delta y to be vy final squared minus vy initial squared. So all of this goes under the basic review from previous topics taught. What we're adding into projectile motion is that a projectile is an object which is moving under the influence only of gravity. I put the little asterisk to that statement, though, that the projectile motion can properly also include air resistance. So this projectile is not just in free fall. There may be air resistance, but we're going to be neglecting that in this course, because if it is moving slowly enough, air resistance is fairly negligible, and if it's moving quickly enough that the air resistance is not negligible, then you're basically working with differential equations. We may treat air resistance briefly in a different video, but not today. So with that caveat aside, what this basically means is that your acceleration is known. So acceleration is thus a in Cartesian would be 0, negative g, where g is free fall acceleration. G is local free fall acceleration. Typically that means that g is about 9.8 meters per second squared. That's on Earth, or near the Earth's surface. The second thing that's notable here is that in addition to knowing the acceleration, you're typically given some other parameters, usually the initial parameters. So often, though not always, initial conditions are known. Now I say often, but not always, because sometimes you know the final conditions and want to predict what the initial conditions may have been. You do have to end up having a little more information in that case, however. For example, you have to know at what time the final condition occurred. So often the initial conditions are known, but in principle we need to know a set of conditions at some time. One little note, although I'm going to be doing stuff in Cartesian coordinates, it's very common for the initial conditions to include an initial position and an initial velocity, and for that initial velocity to be given in polar form. It means that you would have to convert that velocity into Cartesian coordinates before being able to add the vectors if you're using the algebraic approach. The further thing that I would say about this is that that initial velocity is often given for, let's say, like a cannon. So you shoot a ball out of a cannon, and you're typically told something like it has an initial speed of, say, 300 meters per second at an angle of elevation 15 degrees above the horizontal. So you're using horizontal as your x, you're using vertical then as your y. 15 degrees would be counterclockwise from positive x unless stated otherwise, and your initial speed would be like the magnitude of that vector. So what does all this stuff that I've written here actually do to our system of equations that I wrote on the recall page? Well, basically it means that the acceleration is immediately known and we can rewrite our equation. Thus, x, the horizontal position, would become v initial x times time plus x initial. The a sub x term is 0, and so it drops out of the equation. And the 2a delta x equation kind of also goes away because a sub x is 0, so v final x and v initial x are equal. V final x, or vx, maybe I should just write this as the second equation since it is, vx just equals v initial x. Okay, the y parts become, well, basically as we had them before. So, but with now a 1/2 g, so the a sub y is now negative g, times t squared plus v initial y times time plus y initial. And I guess if we're actually writing it in vector form, we probably should just write it like this. But we might represent that as negative 1/2 gt squared because that part is downward. And then your initial velocity in y may be a positive or a negative, and your initial y is typically, though not always, positive. So this would be the scalar versions of these numbers. V sub y, again, is g times t plus vy initial. So that would be represented as essentially negative g times time plus, or possibly minus, but typically plus vy initial. And then you can write something like negative 2a times delta y v final squared minus v initial squared. This one's kind of the caveat of all these equations, because v final, whether it's positive or negative, ends up, when you square it, being positive. And v initial, whether it's positive or negative, ends up being sort of also positive when you've squared it. So this equation I'm putting parenthetically because you kind of have to know what you're doing at this point to make it actually work out. Now, when discussing vector problems, vector addition problems, I've kind of given recipes for how to proceed. Here, it's a little bit harder to give you just a simple recipe in how to proceed because it kind of depends upon what the problem is asking and what your setup is. In other words, you might proceed a little bit differently if you have a projectile motion where you're told such and such projectile is shot across horizontal ground with some initial velocity, figure out where it lands. That's one kind of problem. An entirely different kind of problem might be such and such is shot from off a ledge, even horizontally, figure out where it will land. Another type might be it's shot with some initial, or projected with some initial velocity from a ledge, figure out where it will land. And all of those at least have basically the same approach, which is that you would solve your y equations for time and then use the time in the x equation to figure out how far away the object lands. But you could also have something like such and such is projected off of a ledge and lands at such and such angle and lands this many seconds later. Figure out how high the ledge is and how far away the object lands. That's a valid equation, and you wouldn't necessarily approach it. It's a valid question, and you wouldn't necessarily approach it in the same way as you would the first two. So this is where things kind of fall apart as far as just giving you a simple recipe. You have to start actually problem solving to get your answers here. Now, it is worth noting that these equations are coupled. So equations are coupled. What that basically means is that the time on the set of equations for x and the time on the set of equations for y means the same thing. So these equations are coupled via the time parameter. So if I solve the set of equations for, let's say, the time at which impact occurs, then that time that I've solved for here for y is also the time at which impact occurs for x. And so that would let me solve for how far does the object travel. Alternatively, if I'm told the impact time is 3 seconds after the thing has been projected, then I know that the highest value of t on both sides should be 3 seconds. And so if I want to know what is x when it lands, I'm asking what is x at 3 seconds? What is y at 3 seconds, etc. Also of note is that the y component of the velocity will be 0 at the apex of the motion. This is equivalent to the one-dimensional motion case when we've said if I toss an object straight up into the air, so it's moving initially straight upward, that when it gets to the top of its motion, the speed will be 0. So we have to modify the statement a little bit because the x component may not be 0 anywhere, but the y component will be 0 at the top or apex of a projectile's motion. And again, I'd like to reiterate that how you use these equations, how you use these bits of information, all depend upon the problem that you're trying to solve. So let's go ahead and work maybe one example for this topic. Alright, so suppose that Bill is standing on his balcony out the side of some tall condominium, and his friend is on the ground below, and Bill kicks a ball horizontally so that it leaves the balcony and heads down towards where his friend is standing. We want to know how far away from the building will the ball land. So let's see what information we have. We have that the balcony is 30 meters high, meaning 30 meters above the ground. This is giving us our y initial. We're told that the ball is horizontally moving at 12 meters per second when it leaves the balcony. So this is telling us that our initial velocity, which is v Vx initial and Vy initial is 12,0 meters per second. And then it falls towards the ground below. How far from the building does it land? Okay, so this does it land part on the ground below, these two things together tell us that y equals 0 when it lands. This can be used to figure out what time it lands at. We're told that the balcony is 4 meters wide. This is actually kind of your x initial in some sense. It really means that if I guess you could say if the building's at 0 meters for x, then this is starting off at 4 meters in the x direction. So you have an x initial, you have a y initial, you have a v initial. You have to figure out how far from the building it lands. So this term right here, the thing that we're trying to solve for, this is like your x or your x final. So how do we go about solving these equations? Well, step 1 is solve for time. So first get, let's call it time of flight. So how we do that is we use our vertical equation. Y is 1/2 times g times t squared, that's in the negative direction, plus v initial y time plus y initial. And if we plug in the numbers that we have from this equation, we know that it lands when y is 0, so we're saying 0 is equal to negative 1/2 g t squared plus, and our initial Vy is 0, so we have plus 0 time plus our initial height, which was 30 meters. So if we rearrange everything here, we have that t is equal to 2 times 30 meters divided by g would be 9.8 meters per second squared. Again, this is 9.8 meters per second squared. And this was t squared, so we have to take a square root of everything. So at this point, we would want to put into our calculator, and I got 2.474 for my time. So let's maybe round that. It should be rounded to 2 sig figs ultimately. I'm going to retain, let's say, 3 of them, just so that I can round everything at the end. So I'll kind of underline this 7 to denote that it's kind of an extra digit if we want to retain significant figures. Okay, second step, having just solved for the time of flight, second, use the time of flight. So use the time we found to get x. And so to do that, we'd say x is equal to v initial x times time plus x initial. So again, it had an initial velocity in the x direction of 12 meters per second. So we would use 12 meters per second times the time we just found, which was 2.47. So 2.47. And I actually already have that in my calculator, so I will probably just multiply the number in my calculator by 12. So I will get a slightly different answer than if you've rounded it here. Plus 4 meters. So I multiply the number that I have in my calculator by 12, so times 12, like so. That gives me the first term, and then I add 4 to it, and I get 33.69. So this right here, collectively, 33.69229956 meters. But I need to round this off maybe to 2 significant figures if I'm retaining significant figures, and that would give me 34 meters. If I wanted to enter it into a homework system, those usually have a 1% margin of error from the expected answer. So if it doesn't task on a homework system for significant figures, you'd maybe put 33.7 just to be safe. And that should get you within that 1%. But that's a basic example in 2D kinematics. Now, like I said, there are many other types of examples. I certainly don't have time to do all of them in today's video. That's kind of what studying on your own or doing homework, that kind of thing, is for. But I've given you, I hope, a basic process for walking through one basic problem. I will also add that this is of the type asymmetric motion, and I may have a separate video just to do another example of asymmetric motion in the future. I'm not making one today, though. I will say that the main thing to know about it is, in another video I'm going to introduce a thing called the range equation. That range equation will not be applicable here because the range equation assumes symmetry. And in fact, this is a relatively easier problem because the ball was projected horizontally. Had he kicked it so that it kind of takes flight and does an arc like this, so it kind of does an arc like this before coming to the ground, the problem's a little harder. If I start here, arc up, and land down here somewhere, that problem gets to be a little bit harder because to solve for time, you'd have to go in here and figure out what is VIY. It's not 0. And that means you have an equation that has t squared, t to the first power, and t to the 0th power, which means that you're solving the quadratic equation to get time. So I think those are some basic thoughts to add to projectile motion as a general idea. Hopefully it's enough to get you started on any homework or whatever that you're doing with projectile motion. I hope you've learned something from it in any case, and thanks for watching.